welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see precipitation aging and how to simulate that. Okay, let's understand what is precipitation aging. Okay, this precipitation aging is a special heat treatment. It is basically to increase the strength of the material, strength in the sense yield strength, hardness, things like that. These are basically resistance to plastic deformation. And plastic deformation is the one which is useful for deforming the materials to different shapes. But at the same time, material should not be deformable at certain application conditions. So we need good yield strength, we need good hardness and things like that. So if at all we want to increase this hardness, how do we do that? There are different methods. First is basically to target the basic mechanism of plastic deformation, which is dislocation movement. Okay, so that let us understand what is that and then think about how to stop that, so that we'll understand the mechanism to strengthen, and from there we'll go to precipitation aging. A couple of slides I'm spending on that. First is mechanism of plastic deformation. That is predominantly dislocation motion. Dislocation is a line defect, you may be aware. So in a crystal lattice, if you see, there are line of atoms here and these lines are repeated so that you get this plane of atoms. So there is this continuous plane of atoms, there is this another plane of atoms. But there is one plane which is not continuous, there is a half plane kind of thing here. And if you see the line of atoms, any atom, if you take, let's say the atom here, just one atom behind that, if you see, it has all four neighbors, four sides, and the atom in front and an atom in the back side. So it has six neighbors. So it is nicely bonded according to its equilibrium position it is sitting. Now if you look at this atom here in this bottom of this plane, of plane, below this there is no atom to bond for this. So this atom is not in its most stable form, and in fact the entire line of atoms behind that, okay, just like this line of atoms, there is a line of atom behind this atom, that entire line does not have atoms to bond, okay, below. So the atoms behind this particular front atom, the entire line of atoms do not have atoms to bond on one side. Therefore, this line is a defect. Okay, this is a line defect. We call it a dislocation. And when we talked about dislocation pipe being a faster diffusion path in one of the previous classes, this area is what we have been talking about. This is a dislocation pipe, and this inverted T sort of thing here, this inverted T sort of thing is used to indicate the dislocation. So in a crystal, if I take a grain like this and if I put an inverted T kind of thing like this, it's a dislocation, and if it moves, then the material deforms well. Where it moves within this lattice. Okay, within the crystal it moves, and there are certain specific planes on which it will move. We call it slip plane, and this dislocation motion or slipping of dislocation will be stopped when the dislocation meets a boundary like this. So this is a grain boundary. Beyond that, it is not easy for the dislocation to move. So it will be blocked there. So anything that blocks a dislocation from moving is basically strengthening the material. Okay. So if it is blocked by the grain boundary itself, and we have more grain boundaries in the material by having, let's say, small grain sizes, it's called grain boundary strengthening. Okay. Similarly, there can be a phase like this, and dislocation meets that phase and it will be blocked. Okay, this is a interface. This is also a grain boundary between two phases. We have this interface, and this also can block the dislocation. So if this can block the dislocation, why don't we have this second phase more uniformly distributed in a fine manner like this? Okay, then there are no places, there are no clean areas for the dislocations to move. Wherever dislocation moves, easily it will meet a precipitate particle and it will stop. So this fine uniform distribution of precipitates, the second phase, we call them precipitates. That's one of the effective methods to strengthen the material or block the dislocation. Okay. So when we say strengthening, we basically mean this: if dislocation motion is made difficult, then the deformation is difficult. The lower the ability to deform, the higher the strength. This is what we try to achieve. We are trying to block the dislocation motion by having these precipitates uniformly distributed. Now, finely sized, uniformly distributed precipitates can be effective obstacles for dislocation motion. How do we achieve this? Okay, when homogeneous nucleation happens, it means the rate of nucleation is same everywhere. Then we can get this sort of uniformly distributed particles. Now, what happens in general when we do different processes, it's easier to have heterogeneous nucleation, okay, compared to homogeneous nucleation. So to suppress the heterogeneous nucleation, the matrix is highly supersaturated and then allowed to nucleate the precipitates. So by this high supersaturation, we can achieve this homogeneous nucleation. So for that, we need to do this process called precipitation aging. Let's see how to do that. We can understand it using this aluminum scandium system. One important criteria for precipitation is this. You have a solvus line like this, then at high temperature, this solid is single phase, and if we take a composition like this composition, and keep it at this temperature for a long time, it should have nice single FCC phase. All right, so it's a solution, solid solution, and from there, if we slow cool it, what happens is it enters into this two phase region, and obviously this Al3SC particle will precipitate, but it will precipitate at heterogeneous nucleating sites. Therefore, you will not achieve this uniform distribution of fine particles. What we need to do is, from this temperature, we cool it to somewhere near room temperature. Okay, so this is 200, 250 and so on in degrees Celsius. So I am putting room temperature somewhere here. So at this temperature, quenching, rapid cooling or quenching is done to this temperature. Then it is like taking that FCC at high temperature and putting it in water at room temperature, or anything at lower temperature than room temperature, so that single phase FCC is frozen. It does not nucleate any Al3SC and grow during this cooling. So once we ensure that the single phase solution is formed, it according to equilibrium, this is a two phase region. This Al3SC plus FCC region is going like this. So obviously at this temperature also it's a two phase region. So there, if you see, the solubility in FCC is actually extremely small. Scandium does not dissolve into this aluminum to any significant degree at this temperature. So therefore, what we have here is a supersaturated solution. Okay, because saturation limit is only here, we have a high amount of solute dissolved in it by virtue of freezing the high temperature structure. Therefore, it is a supersaturated one at this temperature. Only at high temperature it is within the solubility limit before the saturation point. At this temperature, it is well beyond the saturation point, therefore it is supersaturated. Once it is supersaturated, definitely it is metastable, because the stable structure, we know it is going to have both the phases. Because it is metastable, it is in a high tendency to become stable microstructure, which is precipitating Al3SC out. If that has to happen, will it wait for heterogeneous nucleating sites to be found? No, it can nucleate everywhere uniformly, that is homogeneous nucleation, and that also requires some activation. Therefore, this temperature 350 degrees Celsius is where it is taken, because at this temperature diffusion is almost negligible. So we bring it to this temperature 350 so that we allow some diffusion to happen. When that some small amount of diffusion is permitted, immediately nucleation starts everywhere uniformly, does not only in the grain boundaries. Then we heat treat it at that temperature for certain time. All this homogeneous nucleation happens, precipitates grow uniformly distributed everywhere, so that the hardness or strength, if you check, it will be maximum after certain time. Okay. Let's summarize what we have seen. Phase diagram nature for precipitation aging. High solubility in high temperature and low solubility in low temperature. That is important. Meaning a solvus line should appear like this. This is a feature of many systems. In all those systems, there is this possibility of dissolving more solute at high temperature and then quenching to make it supersaturated, and then bring it back to a temperature where homogeneous nucleation of precipitate can happen. So solutionizing is the process where you make single solid solution stable, which is this. Okay. Then quenching is done, which is rapid cooling. Rapid cool to room temperature or below, form supersaturated solid solution. So that is the second step. And then heat treat at moderately high temperatures, that is called as aging. Okay. So this high supersaturation results in homogeneous nucleation. That's the key for this process. And peak aging time is the time after which we observe maximum strength or maximum blockage for dislocation movement. Okay. If you do overaging, a longer heat treatment than peak aging time, what happens is larger precipitates grow, consuming the smaller ones. Okay. This phenomena we haven't discussed till now. We talked about impingement and all when growth happens. This is something called as Oswald ripening, meaning a bigger precipitate can grow at the expense of smaller precipitates. Where smaller precipitates have high surface to volume ratio, meaning they have more surface energy. So by making a bigger grain, the total surface to volume ratio comes down. Therefore, the material at the surface, at the grain boundary, comes down. So that's a driving factor for this bigger precipitate to grow over the smaller ones. So that will happen, and when that happens, what happens is this uniform distribution of precipitates is no more available because precipitates have become chunkier and there is large space between these precipitates, and that space is good enough for dislocations to move freely. Therefore, the peak hardness will not be there, peak strength will not be there, it will come down. Okay. Right. Now let's see how to simulate that. We are going to use thermocalc precipitation module. There is an example, worked out example P01, and this example shows couple of diagrams which are different from the same precipitation module example done in the YouTube channel of thermocalc. This channel also has some demonstration videos. In that, the video name is new precipitation module. The channel name is thermocalc. If you go to that video and see, again the same example is worked out, but different final diagrams are drawn and things are explained. So I'm going to do a kind of combination of both of them. Okay, let's see that precipitation of Al3SC. This is going to be the precipitate in FCC matrix of aluminum. This is what we are going to do, and details of the simulation are here. Composition: aluminum with 0.18 mole percent scandium, so very less amount of scandium. It's good enough to give the precipitation aging. Aging temperature is going to be 350 degrees Celsius. Time is 10 power 7 seconds. And as we said, the nucleation should be homogeneous. We'll see how to set it up. Okay. And default values for other options. Let's do that. Okay. So I'm going to go to this example files. Precipitation module TC Prisma. And P01 ALSC AL3SC precipitation. This is the one, that is precipitation aging basically. I open that, wait for a few seconds. Okay, done. I'm also going to click perform first. Right, now the calculation is over. I will show you what has happened. If I click on this system with ALSC system definer, we see two databases are selected, aluminum demo, MAL demo mobility. Then two elements, aluminum scandium are selected. Okay. Then in precipitation calculator, in this stage, we have the setup where you see matrix phase is FCC, composition is here in mole percent, aluminum is 99.82, scandium is 0.18. And in matrix phase, we have FCC A1, precipitate phase Al3SC. Okay, we know this precipitate is going to form. Okay, then nucleation sites, if you see, nucleation sites is selected as bulk, not dislocations, not grain boundaries. It is selected as bulk. This is where we say this is going to be homogeneous nucleation. Okay, so nucleation sites will be bulk, and you can see 10 power 8, 8 point something into e power 28 per meter cube. That is the number of sites. Okay, this is calculated from matrix settings. I'm not going into the details of it. So you can see definitely a large number of nucleating sites are there. Then interfacial energy, so that is also entered. Then in the calculation type, isothermal is chosen and temperature is 350 degrees Celsius. Simulation time is 1 e power 7 seconds. Okay, so once this is set, the calculation is run. Now let's see how the results are. I will show what has come here. Two plot renderers are there with the two experimental data also superimposed. Let me show both of them. Plot renderer 1 is straightforward, where you see the average size of the precipitate. Okay, length is basically the precipitate size, and that with respect to time is drawn here, and this is how the length increases. Okay, so this is average precipitate length. Length means that, okay, so up to 10 power 7 seconds if we go, the size keeps increasing like this. Okay, and experimental points are superimposed. You can see experimental sizes also. So the simulation has very good matching between the experiments, and you can see what is the precipitate size, 1.6 into 10 power minus 8. Okay, it is almost like 60 nanometers. That's the size of the precipitate. Okay, this is what you see as the result. Nice. Now plot renderer 2 I will show later. Before that, I will show couple of more plot renderers. I am going to create, right click on precipitation calculator, create new successor, plot renderer. Okay, now plot renderer 3 has come. In this by default the same length or mean radius of the particle is there. We are going to change this. Okay, so let's keep nucleation rate here. Okay, and axis type, let's keep it logarithmic 10, then visualization will be easier. So nucleation rate of this precipitate in homogeneous nucleation bulk, that is selected here. We'll plot that against time. So this is seconds in logarithmic scale, that is also fine. Now this nucleation rate, if I click perform, you can see how the nucleation rate is. Initially nucleation rate is high and it is constant for some time, meaning continuously nuclei are being generated at some rate, and then beyond certain time nucleation rate decreases, and then beyond certain time there is no more further nucleation. Okay, so this is how the nucleation rate is versus time. Now if we bring some more interesting information which may be very relevant to industrial practices of aging, I will click this plus. This is to add one more y-axis, that's possible. So nucleation rate is already plotted. Against that I am going to put number density. Okay, number density of this Al3SC precipitates will be plotted in one more y-axis with the same x-axis. Okay, click perform. Okay, you can see here. So this side y-axis is now number density, and that is increasing. Okay, increasing as the nucleation rate was constant. Continuously more and more number of precipitate particles are formed, so that is increasing, and beyond certain time, so up to this time it increased to maximum number of particles formed. After that number density starts to come down. Number density is how many particles are there in some unit volume. Okay, and that is coming down here. Okay, so what does it mean? It means precipitate number is coming down and their sizes are actually increasing. Okay, you know what happened to the sizes, the average length of the precipitate which is there in plot renderer 1. Okay, this is length or mean radius of the particles. Mean radius is actually increasing. On an average, the diameter of the particles are going up. It means the larger particles are coming into picture more. That's the meaning. Therefore, you are getting into overaging regime. Okay, that's the problem there. If at all we know the strength values, let's say the hardness is measured throughout these different times of aging, then we will see that the hardness reaches some maximum value and then comes down. Okay, when the overaging happens. In thermocalc, we have some provision for that. If I click on this plot renderer 2, you can see that. See? So this is strength versus time. Okay, this is yield strength, total yield strength. This blue line, these are the experimental points where strength is measured. You can see after some time the strength is coming down. This is where overaging starts. Okay, so we should heat treat only up to this time, not beyond that. That's the meaning of it. How this strength has come into thermocalc, how is it treated here? We will see them when we see about the properties of the material, physical properties and all in one of the future classes. We'll see that. Okay. Right. So other than this precipitation module in thermocalc, we have more softwares. In MatCalc, it's a dedicated software for precipitation. A lot of things can be done in that. And in PanDat, there is Pan Precipitation module. And in QuestTech, there is PrecipiCalc. This is also quite useful for precipitation simulation. Okay. Thank you. I hope the lecture is useful. See you in the next class.